Yeah, so here's where we were. So now the question is, okay, we want our linear congruential generator to produce numbers not between 0 and m, which could be a big number. We just have to find numbers between 0 and 1, right? So what do? You just divide the output by m, right? So that's all I'm doing here. So divided by 256. And I'm going to convert it to digits, right? Dot n digits will give me some digits of precision. So it'll take that rational number and give me some eight digits of precision. So there we go. So now we suddenly have numbers that are looking more like uniform, or they're at least distributed inside the unit interval. So then we can plot it and then see that, yep, it's between 0 and 1 on the y-axis. So then we can now do other things. Okay, let's make a histogram of these numbers, right? So let's see how the histograms look. So this already is getting into the so-called battery of tests of a pseudo-random number generator. We do know it's actually deterministic, right? It's completely deterministic. But then the philosophy is that if I didn't tell you how I'm generating it and I just gave you numbers, then can you, as a user of my sequence, tell me that it's any different from a truly uniform number, okay? So what will you do for this? Well, there's a lot of batteries of tests. I can actually make a histogram and plot how the histogram of the numbers look, right? So that's one simple test. So that's what I'm doing here, just making a histogram. Okay, this looks kind of uniformly distributed, except these little spikes. But this is a small m, right? And there are a lot more tests, right? There are very sophisticated tests that a random number generator should pass. And only when it passes a certain family of tests is it good enough to use for a certain kind of decision, certain kind of decision problem. So this is essentially the main idea. So here let's look at the Knuth's one. After we scale it, it looks like this. Just the same pattern between 0 and 1. But then if you make a histogram of that, it's much worse than the other one, right? Because there are these holes, okay? So that's a bad one. It's obviously bad because it doesn't visit everything. So that sort of gives you some intuition for, if I didn't tell you that it's really a deterministic sequence, can you tell it apart from a truly random uniform 0-1 sequence? We'll see more sophisticated tests soon. So the first thing is making the LCG larger. That means making M much bigger than just 256, okay? So one of these RAND-U is the name of this random number generator. It was released as part of a distribution in many computers in the 70s, I believe. And people were using this, right? And it's this particular LCG. It has a very large M, right? What is this? Oh boy. So 2,147,483,648. It's pretty big. And then it satisfies all the conditions. So now I have RAND-U, and I'm going to take n equals 5010 samples, 5,010 samples. Our same function we wrote works with this. This was shipped with machines, okay? And then when you make a plot, it looks kind of, okay, uniform. I only have 5,010 samples. By the way, the problem of how wide the bins should be when you make a histogram is a pretty open problem in mathematical statistics. It's called the smoothing problem. You see, because if I make the bins too wide, like the whole thing, then I'll get a flat line, right? All the numbers fall in the unit interval, one bin. Or if I have 2 bins or 4 bins, it'll be very smooth. But if I make the bin size very, very small, it's going to get very jaggedy, right? So finding the optimal bin size is actually an open problem even now. Properly, if you think about it mathematically, unless you make assumptions, it's an open problem if you don't know what the underlying distribution is at all. So anyway, that's sort of sidetrack here. So now let's import PyLab and turn the output of this list from LinConGen into a PyLab array. and we're going to call this randu. Okay. So what's the shape of the PyLab array? It's this, single dimensional array, right? So now I'm going to resize the randu array to 2 columns. So this is the second family of tests, okay? So remember we did resize, and now if I ask what's the shape, it's a 2505 by 2 array. So now I plot these two as ordered pairs, okay? The consecutive pairs now. So this is now a plot of these pairs now. I take the original thing, turn them into consecutive pairs. Because why do I want to do this? Because I want my random number generator to produce independent and identical samples from the uniform 0, 1. Right? If it were true, then the first guy has nothing to do with the second guy, right? So if I plot them on the square, unit square, they should be uniformly distributed on the unit square also. Agree with me? It's just what we would expect of a good PRNG, right? And this is how it looks. It's kind of uniformly distributed, right? And what does this mean to be uniformly distributed? If I take a unit, say a square of some area, whatever rectangle, and move it around, the total number of points in that area as I slide it around should roughly be the same, right? That's what the meaning of density is for continuous random variable, the two-dimensional continuous random variable. So it looks like, okay, if I take this big square and move it around, roughly the points look okay. Kind of holes here, but so this gets formalized as a specific batteries test. We won't get too far into it, but just use some plots. So here's the same one. Now I'm reshaping it into 3. Why not? If I take triples at a time, consecutive triples, then will these triples be uniformly distributed in a unit cube, right? That's the next higher dimensional test. So if we do that for this particular randu, there we go. How does that look? Yeah, it kind of looks okay though from this angle, right? But then this is 3 dimensions, right? So let's see if I can find it. There. Now it looks like an Iowa cornfield, So this is a problem with the random number generator randu that was shipped with lots and lots of machines. So people are working on using this for a long time. Found out later. Oops, so you can zoom in and stuff. So anyway, so the formal way of this battery of tests is called equidistributivity, right? And there is actually functions one can write to check how equidistributed linear congruential generator's output is in 1 dimension, 2, 3, 4, and so on. So so randu is a really ugly LCG because it's already busted in 3D, right? Okay. So there is another one that the GNU library uses. This is how many of you play interactive video games, or just video games? Yeah. So this particular LCG is used heavily for rendering, for when you need random number generators to do scene renderings fast. So for scene renderings, this is fine, and this actually is better than randu. It doesn't have these problems, no matter how you look at it. And because video games are just played in 3D over time, so at most 4D, so it's fine for those purposes. So that's a good one for. And why do you use LCG for graphics? Because you just do 1 multiplication or 1 addition modulo m, right? So it's super fast. So just for playing games, it's fine. Okay, so here's just a histogram of it, how it looks. And of course, what I meant earlier is if you change the number of bins, right? That's here, number of bins. So if I make 400 bins, it's going to get really jaggedy. That's what I meant by the smoothing problem, right? Figuring out how many bins you should have. So if I only have, I don't know, 10 bins, it's going to get over smoothed, right? Sorry, under smoothed. And this is called, it's like way too many now. So finding the exact number of bins is, it's a hard problem. My JMOL interpreter is going crazy. I have 2 Docker containers running as well. So anyway, so let's continue. So even good LCGs are not suited for realistic statistical simulation problems. And this means what is realistic here, right? What is the decision problem, or what are you doing with this? Is the question. So yeah, so here is so if an LCG is used to choose points in an n-dimensional space, the points will lie on at most m to the power of 1 over n hyperplanes. This is a property of LCG. So no matter what input parameters you choose, you will always be limited by this fundamental fact. So for high dimensional simulation, LCGs are simply not going to be good, okay? So, but they're really good pedagogical value, and it's good for video games, okay? So you can do simple things like, remember the uniform 0, 1 random variable has mean 1/2. So we can ask, is the mean satisfied? Yeah, it seems pretty good. Variance, yeah, and if you increase the sample size, it should converge to 0.5, and variance should converge to 1 over 12. And that'll happen for a lot of LCGs. So these are simple statistical tests. Okay. Yeah, so, and later on, we will use these properties of linear congruential generators when we further transform them into other random variables to understand what it means to do estimations and what it means to do tests and so on. So that's why we need to build on this knowledge, right? So of course, we will use more sophisticated pseudo-random number generators. So in particular, the default one in a lot of computer programs is called the Mersenne twister, right? So a Mersenne twister is a 623 dimensionally equidistributed uniform pseudo-random number generator, right? It's from the ACM transactions and model. So this is used really well. And the Mersenne twister has a period of 2 to the power of 19937 minus 1, right? So 10 to the power of 6,000. It's a very, very big number, so that's good. But it still has limits that you need to be aware of but you can use multiple Mersenne twisters in a careful way. So people who teach courses on simulation, say industrial process optimization, they will be aware of these constraints. So you may be running parallel Mersenne twisters initiated by different seeds, and then you have to combine them in very proper ways and things like this. But for us, a single Mersenne twister is way more than enough, okay? So you can read more about it. It was developed by Makoto Matsumoto and Tajuki Nishimura, right? And yeah, it's okay. So then, if you find out the source for this file, you can do this. And then, if you actually open this .py random file and look through, you will actually see the source. And that's the other reason we're using SageMath, because everything is open source. So when you guys become fifth-year students and take this course on how to become an entrepreneur, the UU Innovation, you can take your ideas to business right away if you want, right? You can't do that with MATLAB. I mean, you have to pay them licenses. All right, so here's some warm-up before simulating a drunkard's walk. Did you have a question?
Yeah.
Okay, so yeah, this is just to okay, we have uniform numbers, right? Some idea. So we will use the built-in ones, which are essentially the Mersenne twister, which is more sophisticated than an LCG. And then let's do something slightly interesting. So what I want to do is essentially use NumPy's module cumsum, cumulative sum, which we've already used. And then we're going to just simulate a simple random walk. So x0 is, say, the current position or something. Then x0 plus x1 is where you are now, right? So if you say walk -1 to the left, +1 to the right, then by just doing cumulative sum, it's the current position of where you are, right? Say you start at 0. That's a simple random walk in 1 dimension. So that's what we're going to do. And then maybe we'll generalize it to a simple random walk, say somebody moving in Manhattan, right, with grids and avenues, like a grid. So then we can pretend that's the integer lattice, right, in the Z2. And then you go up, right, left, down. So to go right, you will add 1, 0. To go up, you will add the 0, 1, and so on, right? So yeah, that's kind of so this sort of builds up some of the things you've learned. And Okay, I won't go through this. This is kind of a you try, so try it. So it sort of brings a lot of ideas from before. So we're defining probability of going left, probability of going right. And so, these two only sum up to half because I sort of am trying to get you guys to code a two-dimensional walk if you follow the sequel. So I won't, and you're defining functions, make left turn point, make right turn point, and then you're writing movement functions. So this is an interesting concept now. So we have a list of functions, and then we can apply the movement function to create some path starting from a particular point, and then using these probabilities to choose one of these left-right turn things, okay? So I will let you play with this. Yeah, and then in the end you'll get a line plotter, and so it'll give you something that sort of moves around in the plane, and then your idea is to maybe see if you can turn this into a 2D walk. This is not directly an assignment, but it's to help you. Okay, so simple random walk in ZD. So D-dimensional grids are extremely important. There is a mathematical process called the Wiener Process, which is when you take a two-dimensional random walk, or even a 1D random walk for that matter. So say I'm walking, well, okay, so let's say I'm here, I'm going left by adding -1, 0, and then I'm going right by adding 1, 0, right? So if I do this, and then this is say probably half in our quarter, it's probably a quarter in your example, but let's say this is half and half, so it's just a 1D walk. So then I keep moving around, right? Maybe I go here, I come back here, and so on, right? So that's what that plot will show you. But then if you turn this around, right, and pretend that this axis is this axis, and now make this discrete time, then so you're here, and then you moved up, let's say, went up, and then, but that's in the next time step, so you put it here. So this is at time step 1, discrete time step 1. And then you went down again, so maybe you came here in time step 2 and so on. So this kind of thing is called a simple random walk in time. This is another way to visualize it. Maybe you go down again and so on. So anyway, when you take limits of this, when you let the number of steps go to infinity and divide it in the right rate, you get these little things that Einstein formalized, Brownian motion, and then it's mathematically called the Wiener process. So these kinds of things you will learn in some more advanced courses. Okay. Okay, so here is the main remark I started out with. When mathematical models become too complicated to explain a complex phenomena of interest, you have little choice but to resort to modular arithmetic-based simulations with pseudo-random numbers. And then von Neumann invented the first major one, this middle square method, for solving complex problems in the Manhattan Project. So why are we also interested in this? First of all, when we learn statistical inference in a couple of notebooks from now, we will be using simulated data itself, right? We will simulate data according to some fixed parameter, and then we will pretend that this data just was given to us, and then we will apply some inference machinery to estimate the true parameter that the data came from, okay? And that's for pedagogical reasons, but also for debugging reasons. You want to make sure that if you simulated from some known machinery, your method, your estimator, or model fit, actually recovers the true parameters. So that's one of the main reasons. The other main reason is so-called simulation-intensive inference. So this, if you're doing, if you have a bioinformatician in the room, when the mathematical models are too complex for, say, genome sequence analysis, right now pretty much everyone's DNA can be sequenced for like $100 US, or the price is dropping like crazy all the time. So we have the full genomes of everyone for very little money, right? There are entire populations that the whole population's genomes are sequenced, right? So now when you try to make sense of how these genomes are inside people, and then when, if you run the movie backwards, I go back to New Zealand, and then I was born in India, and then I would came out of my mom, and before that, before I was a differentiated, adult or body, I just chased my blastula all the way, and then I'm a zygote, right? My DNA is still there, right? It's just copied through mitosis. And then I ask, where I'm still my DNA is there. It's definitely not Raz, right? I don't have my name or anything. But then you can ask, where do I go from there? Well, you can actually go further, right? Because my nuclear DNA comes from my dad's sperm, my mom's egg, right? And my mom's egg was there when she was born, and my dad's sperm entered, right? So I can chase the parts of the DNA that came from my dad and that came from my mom, and then my mom's, so my more and my more force DNA did recombination to produce her egg, and the same with my dad, right? So it gets to be a very complex process. This is called the pedigree process. And so for that, you also do incredibly simulation-intensive inference, right? So this is for hunting diseases, like rare diseases and all sorts of things. You guys probably won't do it. That's something I do, so I know about it. Okay, so here is something I did just now. I have this grant with some Israelis on how to guarantee privacy for citizens in Israel and anywhere when you have access to mobile phone records for the whole nation, let's say. So you know exactly where people are in some high resolution of time and space. And then how do you prevent an adversary from actually acquiring this information and finding out who you are? This is a very interesting current problem on privacy-aware decisions. So I just did some simulations in a big hurry one day at a boring seminar. So this one is trying to do like a random walk, except just instead of 1D, I now have a 2D random walk. Okay, so I put a bunch of population of individuals. Each one is doing a random walk in 2D, and I'm showing it through time, right? So people are, just imagine it's an open field and it's not people. I don't know, some creatures are randomly moving around, right? And yeah, you can sort of try to understand, anyway, this is just a simulation, but you can try and understand what is inside this function. You guys know all of the different components here already. Okay, so this is just a recommended exercise in commenting this. Yeah, you can just try to understand if you want. Okay, so let's continue with 8. Are there any questions up to now? Okay, good. So all we did is, how do we take pseudo-random numbers, which are giving samples in 0, 1, and then just turning them into simulations. And when you go through this U-try in detail, what you will find is to decide, the probability half. All we're going to do is, if my pseudo-random number is between 0 and a half, if it takes any values here, then I will choose this as my decision, turn left, for example. And if it's between exactly half and 1, then I will choose this decision, right? And the way it's actually coded is a bit more interesting. So it's quarter, 3/4. So this quarter is actually one of these, and this one is for this part. And then you're supposed to try to, code for this part. If the random PRNGs fall here or here, you're supposed to make this a 2D walk, right? That's why we have 2 axes. So then, if it falls here, maybe you should go up, which is what, +1 or 0, +1. And then if it falls here, this one, right? Which is x-axis is 0, y-axis is 1. So now this intuition of how to transform samples from the unit interval coming from a PRNG sequence, pseudo-random number sequence, into a simple random walk, we want to generalize that idea, okay? We want to take samples from PRNG and get, like, say, exponential random variables, right? Or Gaussian, or whatever. So how do we do that? That's the main point of this notebook. So simulating from some discrete and continuous random variables. So we will see uniform 0, 1, the Bernoulli theta random variable, equiprobable de Moivre K random variable, and simulating from it uniform theta 1, theta 2 random variable, simulating from it exponential lambda Cauchy, which is a very important random variable, how to simulate from. So these are kind of really nice basic ones on top of uniform. Okay, so that's the plan. So we have x1 through xn, independent and identically distributed according to uniform 0, 1. And how do we transform it? So let's recall this is the density, probability density function, and the distribution function for uniform 0, 1. And this guy we said is what that is. So now we can produce a list of 3, and that's my 3 numbers. Well, the point is, if we do this again, we'll get a different sample, right? So we need to control it. How do we control it? It's a deterministic sequence, right? So you control it with where you started, right? That's called the seed of the pseudo-random stream, right? So we had that as a parameter even in our LCG, right? So that's all. So so if you ask set random seed, the doc string for that, it says set the current random number seed from the given seed. Okay. Yeah, so it's Python long coercible. You know what coercible means? To force someone, to coerce them to do something. So I mean coercible means it must be typecastable into integer long, because the pseudo-random number generators that are under the hood, they are operating on long integer space, integer longs. So it's just the output comes as digits. So the seed is always long coercible. Okay, so you can do this. So now I've set a random seed. So now if I ask this, it'll give me this sample, right? Now if I ask what's the initial seed, it'll give me whatever I was set. It puts a L because it's already converted to a long, that's all. Okay. So now, so the point is, if I ask what this is again, if I go and evaluate it again, it'll be exactly the same. Oh, no, of course not. The seed changed. So there we go. So if I do that, it'll be exactly the same. And that's the point here. So we have to set random seed and then produce this sample. So now it's going to be the same as this. You see? Okay, so then whatever you do from then on will be reproducible from this particular seed. And you can always ask what this is, and it's the same. So you can set random seed to be a different one, and then you will get a different sequence. And so at least you're encouraged to test your algorithms that it takes the random numbers as input on at least 2 different seeds, and the behavior should be reasonable under different seeds, right? And also controlling the seed will help you debug everything. So you know exactly what numbers will come out, and so you can debug it. Okay, so here's just some samples. We're comparing visually with 2 different seeds. So seed 1 is in blue and seed 2 is in red. And then now I'm just superimposing samples from seed 1 and seed 2. So it's, yeah. Okay, so here's a little U-try. Now let's look into the Bernoulli theta random variable, right? So that's the question. What can we do with uniform 0, 1? Why bother? Well, let's do Bernoulli. So in Bernoulli, we have a parameter theta, right? And the mass function is theta if x is 1, 1 minus theta if x is 0, and 0 otherwise. And that's the distribution function. So we can just define this. We've already done this before. So Bernoulli PDF and CDF. So if you guys looked ahead in the notebook, you will have the solution for the last exercise, right? So this is one way to do it. So, and then I'm just putting some functions here, just plotting make free predict, make empirical mass functions. So these are some helper functions. All these things you've seen before. So I just want to evaluate, bring them all in place in this notebook now. So it's all in the kernel that's running currently. So now we can see the effect of varying theta interactively, right? So this is my Bernoulli theta random variable, and the probability mass function is here, and the distribution function is there. So, okay, so that's the So simulating a sample from Bernoulli is like this. So what we need to understand this concept of a floor of a number. So floor of a number is the largest integer smaller than that number. So floor of 3.8 is 3. So and here is the pseudocode, the algorithm for simulation. So the input is going to be U, which is a uniform 0, 1 from a PRNG. And the other input will be the theta, the parameter for the Bernoulli. Okay? And then this tilde symbol means sample from in statistics. Output is little x, which is a sample from Bernoulli theta. That's what we want. And here are the steps. So this is like the sort of simple way to explain an algorithm. Right? Input, output, and the steps in the body of the function. So we first, U gets uniform 0, 1. This is pseudocode for assignment operation. So we do C or C++. It doesn't matter what language, Scala, Java. This is just a generic symbol for assignment. And X gets U plus theta. In R, this is used as less than dash in R, right? And then X is now going to be the floor of U plus theta. Okay? And then you return X. Do you guys see why the floor of U plus theta should work for Bernoulli? So let's make a picture. So U is going to be my PRNG. It's going to be some number here, right? So U will be something random here. So what is it saying? U plus theta. So I add theta. Let's say theta is 3/4, right? So if this is U, that's how wide, how big U is. So if I add theta to it, it's going to be I don't know. Let's say it ended up here. So let's say this is something like 0.9. Okay, so this is 0.75. So then I add theta to it, right? So theta is a parameter for the Bernoulli, it's fixed. So now what do I have? What is this number? What is 0.9 plus 0.75?
1.65.
Good. 1.65. And then I need the floor of it, right? So floor of this is going to be, so it'll give me 1, right? Which is a Bernoulli thing. And if say U is really small, let's say if U is, so I'll call this U prime, say this is 0.1, then 0.1 plus 0.75 is going to be 0.85, right? So, so what's the floor of 0.85? 0, right? So U prime will actually, if U prime is here, it will give you 0. If U is here, it's going to give you 1, right? So if you think about this, all it is doing is simply, dividing the unit interval into, things of size theta, and everything that maps there will get bumped up by theta, and then it'll get back to 1. Okay, so that's all this is, and we can simply do it like this. Theta is half, U is random, X is floor of U plus random. Okay, so of course if I try it again, it might be 0, sometimes 1, okay? So to make a number of simulations, we can use list comprehension like this, floor of U plus theta, boom. I now have a list comprehended Bernoulli fair coin toss from my uniform 0, 1. Okay, so let's make some functions to make this a bit more, I don't know what Python's going to do. So what is this? So I'm defining the inverse of the Bernoulli. So it's a function to evaluate the inverse CDF of Bernoulli. I take the distribution function now, not the mass function, and then I invert it. So if I invert it, what I actually have is floor of u plus theta. So this is my distribution function view. So what is it? Let's say this is 0. So at 0, it's 0, and then it jumps to 1 minus theta, right? Okay, 1 minus theta, and then it continues, and then at 1, it jumps to 1, right? Right, that's the distribution function. So what I'm basically saying is that if I think about the inverse distribution function, right? Let's keep the parameter. What is that? That takes a u, say u falls here, and then it's going to invert it, right? So if u falls anywhere here, the way the inverse is defined is for this supremal value. So any value here will get mapped here, and right. So any of these u's will go here and get mapped here, and any of these u's will actually get mapped here. So this inverse is the floor of u plus theta. Okay. And this is fundamental theorem of simulation, right? There's a more sophisticated version of this called the inversion sampler due to von Neumann. That is the real thing, but this is almost the real thing when you can do it. So now I have Bernoulli F inverse defined, and then I'm going to have a function called Bernoulli sample n theta. So it'll simulate n Bernoulli samples, n samples from the Bernoulli distribution. Okay, and I'm just doing my list comprehension. I first produce a list of views, and then I comprehend it using my F inverse function. Okay. Okay, so let's do that. And voila. So now we're doing this. And here is an interact. So you can sort of play around with data, and then you can look at the samples. So I want 10 samples or whatever. So what I'm plotting here is just the empirical distribution function for the 10 samples. So if I make the sample size very small, right? So the probability mass function is plotted here. No, what's this? Yeah, it's the empirical probability mass function and the empirical cumulative distribution function. That means you take the actual samples and see what fraction of them are zeros, what fraction are ones on here, and then what fraction are zeros and ones here. So because theta is very large, most of them are landing here. So if I make theta like this, see, roughly 60% are zeros in the simulation. And if I increase this, this is going to get very close, bang on 0.6 and 0.4. So we'll visit these later on as theorems and probability, but the simulations are just there. Okay, so let's continue with this. Okay, so this is just a U-try for you to continue. So this is the next main idea, right? Equiprobable de Moivre theta random variable. So here I actually have 1 over k, 1 over k, 1 over k, right? This is rolling a die problem. So here the idea is basically identical. So let's first look at the CDF and PDF or PMF mass functions. So they're all 6 outcomes for the die have equal probability, and that's the distribution function. So now how do I do this? This is already straightforward, right? U's will fall here uniformly at random. I just have to say all the U's are between 0 and 0.2. I map to 1, between 0.2 and 0.4 I map here and so on. That's what we were implicitly doing on the 2D random walk. We had a de Moivre random variable with 4 outcomes, left, right, up, down. But the outcomes were on the Z2 there. orthonormal basis vectors. Okay, so here is some simple simulations from the same idea. Now you see you do floor of u times k plus 1. Why? I mean, the picture should be also straightforward. I have u, right, between 0 and 1. U falls somewhere here. So I just multiply this by k. Right? So I stretch this. So if the u is close to 1, it'll get stretched to k. Right? So k can be 6 or whatever. Right? And then if it's at half, it'll get stretched to k over 2 and so on. Right? Say 3. So I first stretch it and then I floor it. So this plus 1 is there because the Moivre is defined as the first outcome being 1. Okay. So that's, and here is the pseudocode for it. You just have floor of u times k plus 1, and here are the implementations for it. Okay. So then you can just simulate like that. So here's the interact. And once again, in the interact, you can choose k to be something, and you're looking at the empirical relative frequency, or the empirical mass function, and then the empirical distribution function. So as the increased sample size, you see they're getting closer and closer to 1 over 6. And yeah. And of course, I can increase k and so on. Right? All right. So when k is 1, right? When k is 2, we have a problem, right? This looks almost like a Bernoulli, but it's not quite a Bernoulli, right? Because when k is 2 in the de Moivre, the first outcome is 1, the second outcome is 2, right? But in the Bernoulli half-half, the first outcome is 0, the second outcome is 1, right? So that's why the mean, the variance, everything will have different numbers. All right, I'll see you guys tomorrow.
Tjena, jag var vem ropar. Är det bra? Ja, det är så jävla trött. Ja. Det går att vara... Det går jättebra. Det går bra. Det är slitsamt. Ja, det är det. Men jag har ju dragit på mig ett till sak. Jag ska vara redo på.